So Unit 4 deals with projectile motion. Now, projectile motion is something that we are already familiar with every day, especially if you're playing sports, okay? And in long time ago, when I guess pre-Galileo, okay, people thought when you actually like fire a cannon or shoot an arrow, right, they thought the cannonball would actually go straight like so, and then when it runs out of impetus, it would just fall straight down. And that's what they thought. And people were like, oh, okay. Right? They never really questioned it. Until Galileo came by and says, no. I never seen a cannonball go straight up like this and then straight and then like it just fall straight down. You could clearly observe something by looking at a ball being thrown, and it would travel in an arc, like a parabolic path, right? And a curved path, because you could observe that. Okay? So he actually went on and tried to explain how curved paths happen because of acceleration due to gravity is happening. But he did not know what gravity was. But he just knew things move faster and faster and faster in the y direction. Okay? And projectile motion pretty much incorporates both x and y motions simultaneously. Okay? We are already familiar with the vertical motion of an object being thrown straight up, okay? Or just being dropped, or thrown down, right? And anytime when we have a vertical motion, that vertical motion is always affected by gravity, and it will make things accelerate towards the center of the earth at negative 10 meters per second every second. Okay? And we also studied motion in horizontal motion, right? And horizontal motion, when things are moving horizontally, okay? In projectile motion, it is moving at a constant speed because there's no acceleration happening horizontally, unless you like put a jetpack on this soccer ball or some kind of a propellant or engine, right? But unless you do that, the horizontal motion of a projectile motion will move in a constant velocity, right? This will cause the vertical motion to drift sideways, if you think of it that way. Okay? So, if I were to watch a soccer ball being kicked, let's say Kate kicks the soccer ball towards me, right? And I am like really far away from her at the other end of the field. And Kate is just like, just nonchalantly passing towards me, right? Like so. When I see that soccer ball, it looks like nothing really different than just going straight up and coming down if I'm looking at it from really far away. You know what I mean? It'll look like for me, it'll look like it's just going up and then come back down. Because that's exactly the same behavior I would see if I'm looking at the soccer ball far away. Similarly, as Kate is kicking the soccer ball, let's say I am at cloud number 17 looking down, really far up. There'll be no difference of this soccer ball just going across the field versus doing this, because I wouldn't be able to tell the difference, right? So the vertical and horizontal motion can be analyzed completely independently from each other. Okay? So let's write that down, right? So the vertical motion and the horizontal motion are completely independent of each other. However, there's one common item between the two, and that is time. Time is the only common thing, right, between the two. Okay? So we can analyze horizontal motion completely separate from the vertical motion, but the time is the only thing that a common factor that can be applied to both motions. Okay? All right. So if we were to look at this a little bit more mathematically, okay? A little bit more mathematically, I can see that, wow, okay. This projectile motion is basically the same thing as the free fall motion, but sort of drifting to the right. Okay? So if I were to, let's say, launch a cannonball or kick a soccer ball at this angle with this initial velocity of v naught, right? This is this v naught. This v naught is the initial velocity. Okay? Sometimes is known as the muzzle velocity if you're like shooting it from a gun or a cannon. Okay? Or if you're like launching it with like, you know, a soccer ball or like launching something at an angle, initial velocity is v naught. This theta naught is known as the launch angle. And that determines how this v naught can be broken up into its components of Vix and Viy. Okay? This Vix right here is known as the initial velocity in the x direction, so Vix. This Vix can be calculated using this hypotenuse v naught, right? And this launch angle theta naught. So Vix is simply v naught times cosine of theta naught. Okay? This is your initial velocity in the x direction. And this Vix, well, we'll talk about that later. Let's take a look at the Vy naught, right? Vy naught. This is the y component of v naught, which is the vertical component of your initial velocity v naught. This vertical component, Vy naught, is Viy, so initial velocity in the y direction, and that can be calculated using this hypotenuse v naught times sine of theta naught. So this is very important to know for this projectile motion. Okay? So if we split up the direction, x and y direction, so x direction is the horizontal direction, obviously, and this x direction, we can use constant acceleration equation, okay? But your acceleration in the x direction is 0. There's no acceleration in the x direction, which makes your constant acceleration equation in the x direction very, very easy. So if you look at this, if you look at this equation right here, let's take a look at the first equation. Vf is equal to Vi plus At. My acceleration is 0, so this goes to 0, which will make, right, Vfx is equal to just Vix. So my first equation, equation number 1, becomes my Vfx is equal to simply Vix, because my acceleration in the x is 0. That means no matter what time, my velocity in the x direction will always be exactly same as my initial velocity in x. Okay? So my Vix, right, is constant. The whole time. So no matter where it is along the trajectory, this Vix that we calculated here in the beginning stays the same no matter what. So in the x direction velocity will always be my Vix. 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 So x direction is easy. Now let's take a look at what happens for my second equation. My second equation is this, and my acceleration in the x direction is 0. Therefore, my second equation, delta x, now just becomes simply Vix times time t. So this is equation 1 and this is equation 2. Okay? Well, that's very convenient. Okay? That's very convenient. So if I were to look at this delta x, this whole delta x right here from the beginning to finish, that delta x can be represented as the range. Okay? And range now can be found by Vix times t total. Total time. Okay? Now the third equation, obviously if this is 0, then this whole term drops out. That makes Vf squared is equal to Vi squared, which basically turns out to be that, right? If you take square root of both sides. So that's kind of trivial. All right? So, boom. So this range can be calculated by multiplying the initial velocity in x times the total time of the flight. Now let's take a look at the y direction. For the y direction, you definitely have acceleration in the y direction because of gravity. Gravity will make things accelerate towards the center of the earth at negative 10 meters per second square y hat. For your lab, however, you really should use negative 9.8 to be more accurate and precise. Okay, don't use 10. Okay? So, because of acceleration doesn't go away, your first equation, this is your equation 1, right? Goes on tight. It's just basically VFY is equal to VIY plus negative 10 times t. So this does not go away. And your second equation, this is equation number 2, right? Your y final is equal to y initial plus VIY times time plus 1/2 negative 10t squared. And of course, you can also use equation number 3 when you don't have time, which is simply VFY squared is equal to VIY squared plus 2 times negative 10 times y final minus y initial, or your delta y. All right? So you can use these 3 equations here to solve a lot of things. Then once you know those, you can use that to here. So most likely you could solve time using the y direction and use that time to figure out the range, because you already know what the velocity is at any time in the x direction. Okay? So for y, notice what happens. This is your y initial, and as it goes up, it's going to slow down, slow down, slow down, and when it reaches the maximum height, so at y max, right, your Vy is equal to 0. Right? At y max, your Vy is 0. Instantaneously. And then, now it's coming down. Now it's coming down, but now with greater speed going down. Okay? So your velocity in the y direction will change depending on what time it is. However, in the x direction, it stays constant. So, let's take a look at this range, right? Range. So, I'm going to go over this range equation. You do not have to memorize this, or you do not have to actually use this. The only reason why I'm using this range equation is to do something else much more important, which is what angle do I shoot to get the maximum range? All right? So that's what I'm going to do. So here, projectile ground level to ground level. What does that mean? That means my initial starting position in y is 0, and my final position in y is also 0, which means my delta y is equal to 0. Okay? And that's the range equation. So don't use this. I'm just doing it just to prove something. Okay? So this delta x from here to here is the range. Okay? To show you what I mean by that is, if I use the equation number 2 for the y direction, now notice I'm using y's with my aquamarine blue to represent air and sky, and I'm using my green as my green field along the grass horizontal, right? So I'm trying to do color-coded there. Here, my final position in y is 0, and my initial position in y is also 0. And this here is my VIY, which is same thing as V naught sine theta, right? Plus 1/2 GT squared, where G is equal to negative 9.8 meters per second squared. Okay? So if I plug in 0 here, I get my 0. Okay? And then if I factor out a t from here and factor out a t from here, what I have here is V naught sine theta plus 1/2 GT, because t is here and taken out and t here is taken out. So if I solve for time to make this equation true, t can either equal to 0 or it can equal to this whole thing set it equal to 0, and you'll get that. Right? Or t is equal to 2 times v naught sine theta naught over negative g. So this is the time it's going to take to travel from here to here. So now if I substitute that time, this is t total by the way, right? This is t total. If I substitute that time to my equation number 2 for the x, which is delta x is equal to vix times t total. So if I substitute that into here, my delta x becomes vix, which is simply v naught cosine theta naught times this whole mess, right? 2 v naught sine theta naught over negative g. That basically is this. So I can multiply these two v naughts together and I get v naught squared. Then 2 times cosine theta sine theta right here. There's an identity where 2 cosine theta sine theta is equal to sine of 2 theta, this double angle theorem. So I can supplement this identity into here, and then this is what I get. Okay? This is known as the range equation. Now, what's important about this? Okay, so where g is equal to negative 9.8 meters per second squared. Okay? So notice, if I put negative 9.8 here, this negative will cancel out that negative, giving you a positive value. If I look at the sine graph, this right here, I mean, this is constant, this is constant, this is the only thing that changes. But what is the maximum value of sine function? One. Yeah, 1. And where does that happen? If you look at a sine function, where does that maximum of 1 happen for the sine function? Pi over 2. Or, what is the angle-wise, degree-wise? Pi over 2 is 90 degrees. It happens at 90 degrees. Right? It happens at 90 degrees. Therefore, to make this maximum range, what should your theta be to make this a sine of 90? What should this theta be? Because it's 2 times theta here, right? So what should your theta be to make it 45 degrees? So, if you kick a soccer ball at 45 degrees, you will get the maximum range. You will get the maximum range. If you throw something at 45 degrees, you will get the maximum distance. Right? Now, of course, this is true in vacuum. In real life, if you throw a football, it does have that little bit of lift because of aerodynamics. So you want to keep it like 43.7 degrees, I think, to make it maximum. I know, but only like the MIT football players can do that. Does MIT have a football team? Yes, it's Division Pi. Yeah. So yeah, they're not even Division 1. They're Division Pi. So if you were to look at this sine function, the maximum value of sine is 1, and that happens at 90 degrees. So to make this true, to make this true, your theta must be 45 degrees to get a maximum range. Okay, so the 45 degree will give you the maximum range, which is this right here, right? So this is 45 degrees. That will be the maximum range, right? Anything less than 45 degrees will not go as high, or will not go as far, actually, right? But if you were to actually shoot this at complementary angle, which is 60 degrees, you'll get the exact same range. You'll get the exact same range as your 30 degree angle. But it would just go up higher and then come back down. Okay? And if you go at 15 degrees, it will not go as far. But if you do it at a complementary angle of 15, which is 75, this will go really high up and it will come back down like this. So if you have to, like, you know, use a lob wedge to make it go high over the bush to land on the green, right? You want to go up the complementary angle rather than going through the bush. You may not find your ball, right, if you do it this way. All right? So it's a good idea to know this because you never know. You know, you could be using this, right? Because, like, Kate, when you have to, like, pass a ball and there's a defender right here, you have to quickly calculate that you have to kick the ball at a complementary angle to go over the defender rather than going through the defender, right? So, very useful. All right? All right. So, any questions? That's the only reason why I derived the range equation for you. You don't have to learn how to use it. You don't even have to know how to derive it. All right? So I only did that. The key point is 45 degree will give you the maximum range. Okay? Now, I will take a look at the next here. All right? So we have, let's say, a projectile motion of dropping versus shooting. Okay? Let's say we fire a gun horizontally. Horizontally. That means at 0 degrees. If there were no gravity, this bullet will go straight horizontally. However, because of gravity, this will fall back towards the earth in a curved path like such. If I were to fire a gun horizontally and from the same height drop a bullet simultaneously as the gun is being fired, which bullet will hit the ground first? The one that's dropped or the one that's fired from a gun? How many say dropped? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. How many say the one fired from the gun? One brave soul. How many say at the same time? You can't vote twice. You could, 2 people say same time. Well, let's take a look at this video of Mythbusters. Yeah, they actually did this experiment, right? So, both bullets, okay, because gravity will work on both bullets exactly the same. And since the bullet is fired horizontally, the initial velocity of both bullets in the y direction is 0. Okay? So because one fired horizontally behaves just like one is being dropped vertically, it will behave exactly the same way. The horizontal motion, whether I fire this thing at a slow speed or medium speed or very fast speed, the only difference is the medium speed will go further in x direction before it hits the ground, but it will still hit the ground at the same time as the slow speed versus very fast speed. The bullet will go much, much further horizontally before it hits the ground, but they still will hit the ground at the same time. All right? And again, that's only if you fire the gun horizontally at 0 degrees. Okay? So, let's see Mythbusters. Okay? So we got that out of the way. All right? The next one is pretty interesting. Okay? This problem came along a long time ago. The legend has it that a Harvard anthropologist were seeking this indigenous tribe where they were completely isolated from modern world. And they wanted to go study how they live and how they eat and all that. And they actually found them. And when they found them, the indigenous tribe men would go out and hunt for food. And one of the foods for protein were monkeys. They were small monkeys. And they would hunt them. And the way they hunted them was they would bring an arrow or blowgun, and they would wait until the monkey drops from one branch to another branch. So monkey, realizing they're being hunted, they would try to escape by releasing their grip from one branch and try to drop down to the next branch trying to escape. But as soon as they released the grip, they would shoot the monkey and they would get a hit every time. So these anthropologists were like, oh my God, I'm blown away by this. How do they hit these monkeys? They're like incredible, like snipers, and they must know physics, or they must know something, right? So they brought that back to Harvard and asked the physicist and saying, yeah, these indigenous tribe guys, they were able to hit these monkeys mid-air when they were falling down. And of course the physicist said well, yeah, of course. It's a lot easier to hit a monkey when they're falling down than if they're just holding on to the branch. And they were like, what? Because the arrow and the monkey will be affected by gravity exactly the same way. So as soon as they let go, the arrow would shot and it would actually meet the monkey because of vertical gravity will actually work the exact same to both. Okay? So let's take a look at the actual demonstration of that. So projectile motion, stationary launcher, right? From high altitude to low. So here's example 1, horizontal initial velocity. So we're shooting this at 0 degrees. So here my theta naught is 0 degrees. Okay? I am looking for V naught. So this thing is fired horizontally at V naught. And that V naught is actually your VIX. Because you are shooting it horizontally, that means your VIY is 0. Okay? So horizontal means your VIY is equal to 0. So when this thing is fired, it will actually travel in an arc as such, right? And it will hit the ground as such. There goes the neighborhood, right? Therefore, we need to find out what this V naught is, which is your VIX, which is your muzzle velocity. Okay? So a cannon is fired 50 meters above the ground. So this is your Y initial, and your Y initial is 50 meters. And your Y final happens to be 0 meters. Okay? You are told that it hits the ground 320 meters from the base of the cliff. So this is your range, which is your delta X, which is equal to 320 meters. Okay? It says here, A, calculate the time the ball is in the air. So what they're really looking for is, they're looking for time, T total. Right? The total time is what they're looking for. So let's write down everything we know in the Y direction. So we know my initial position that we fired this cannon from is 50 meters. My final position for my Y direction is 0 meters. I know my VIY for this cannonball is 0 meters per second because it is fired horizontally, right? And my theta naught is also equal to 0 degrees, and my A sub y, which is equal to G, and I will use negative 9.8 meters per second squared here because I want you to be very accurate and be very precise with this lab. Instead of using negative 10, use negative 9.8. Okay? Therefore, if I were to use equation number 2 in the Y direction, which is your Y final is equal to Y initial plus VIY T total, right, plus 1/2 A sub Y T total squared. So now if I plug in the right values, my Y final, 0, is equal to Y initial, 50, plus initial velocity in Y is 0, so 0. 0 times T total is still 0, so this whole term drops out, right? Plus 1/2 times negative 9.8 times T total squared. So 0 is equal to 50 minus 4.9 T total squared. So 4.9 T total squared is equal to 50. So T total is equal to plus or minus square root of 50 over 4.9, and that comes out to, right, 3.19 seconds. Obviously it's positive or negative, but you're going to pick the positive time. So this is T total. Okay, that's the total time that cannonball is up in the air. So what about part B? Calculate the speed of the cannonball as it exits from the cannon. So this speed right here is basically your VIX, which is your muzzle velocity V naught, right? And that's what we're looking for. So if we look for VIX, that is the V naught. So to do that, we can say, well, delta X, again, using equation number 2 in the X direction, my delta X is equal to, we already said here earlier, right here, right, that delta X, which is the range, is equal to VIX times T total, right? So my delta X, which is the range, is equal to, right, VIX times T total. So we already know what delta x is, and delta x is 320 meters, and we're looking for VIX. We already know t total, which is 3.19 seconds. So if we solve for VIX, right, VIX is equal to now simply 100.3 meters per second. And that is your V naught. That is the muzzle velocity. So all you need is the time and the height to figure out your muzzle velocity of your cannon. Alright, now it says, calculate the time it takes the cannonball to travel 3/4 of your delta x. So your new delta x at 3/4 of delta x is equal to simply 0.75 times delta x, your range, right? So delta x is 3/4 of 320 meters, which is equal to, right, 240 meters. So that will be somewhere here. So I'm just going to roughly say that is your delta x of 3/4 of delta x, right? But they want to know how much time it takes to reach that. Well, we can use this equation again, but we don't have to really use total delta x. We just use, right, delta x 3/4 is equal to, your VIX does not change, but now you are looking for the time at 3/4, right? Therefore, instead of 320, I use 240 is equal to, your VIX, we calculated to be 100.3, times that by t at 3/4. So if I solve for t at 3/4 away of delta x, that should come out to 2.39 seconds. Are we good? Alright. Alright. So, now they're asking to calculate the height y position. So they want you to calculate how high this thing is here when, right, t is equal to, they want to know what this y position is, right? Y final at 3/4 of time. Okay? So you can use the second equation, y final is equal to y initial plus v I y t at 3/4 of time plus 1/2 a sub y t 3/4 squared. So here I'm looking for this y final at 3/4, right? And that is equal to y initial is 50 plus 0, because initial velocity y is still 0, plus 1/2 times negative 9.8 times your t at 3/4 is 2.39 seconds, right? So 2.39 squared is what you have. So this turns into simply 50 minus 27.99, and that is equal to 22.01 meters above ground. Then they ask you to calculate this final velocity right here, right? this final velocity, v final, at 3/4 is equal to this vfx at 3/4 and vfy at 3/4. But vfx is easy. We already know that, right? And they want us to calculate the theta, right? So we know vfx is equal to vix, no matter what time it is. It doesn't matter. So your vfx at any time is 100.3 meters per second, xhep. However, VFY, we have to calculate. We'll finish this up on Friday.